Hey guys, so wanted to get you a video for today's class since I won't be seeing any of you. The last videos that you guys should have watched, hopefully you are about classes of matter and phases of matter. And then before that, we did the scientific method and we did the branches of chem. So nothing crazy, just working our way through that PowerPoint. All right, so the one from today also includes two topics. I want to look at chemical reactions, and I want to look at your types of elements, all right, different categories of elements that we'll see. All right, so with that in mind, all right, I'm going to share my screen with you guys. And take you to the PowerPoint. All right, so we just finished up talking about states of matter, and we said that everything there is all about how close the particles are, right? Solids have strong attraction forces, so their particles are close together. All right, gases, particles are far apart because they have the least attraction, right? And liquids lie somewhere in the middle. So we got those three characteristics. With the solid, we had the definite shape, definite volume. With the liquid, we got our definite volume, but we didn't get definite shape, and our gas, we got neither. All right, so when we start talking about characteristics of reactions and physical properties and chemical properties and physical changes and chemical changes, there's a couple facets to that. Right? The first category of things that we can measure, we'll say, are physical things. Right? These are things that mostly are describing how you look, and you can measure them and test for them without altering the identity of the sample. All right. If we were talking about a person, physical characteristics of that person would be something like their height, their weight, all right, their eye color, right, descriptors. Right? Chemical properties, right, are things that if we test for them and they have that property, it's going to transform it into something different. And once we transform it, we can't get it back to the original substance. All right, so your chemical changes usually include things like burning. I can test if my skin is flammable, but if it is, I'm going to change my skin cells into a burnt mess that I can't get back. All right, that's a chemical property. All right, so it's not simply describing what it looks like, it's describing either how it will behave, or right, it's describing how it's going to react with something else. All right, so if we're looking at chemistry ones, physical properties include things like melting it, boiling it, its mass, its density, its color, things like that. Chemical properties, flammability and reactivity are the two big ones. Will it react with this other substance? If it does, and it has that property, I can't get it back. It's going to go. If it doesn't, then I know it's non-reactive and it won't change, right? So a chemical property is one that lets it change into something else. Right, now, when we measure these things, a lot of times we'll be getting numeric values, right, in them. Right? Now, when we get number values, that kicks into two other categories of properties: extensive, which you see up top, and intensive. Extensive properties, the number value that you would record depends on how big of a substance you tested. Right? Mass is one of them. For instance, right, if I gave you, right, a piece of paper and said, oh, go record this thing's mass, and you went back and put it on the balance, you would get some number. But if I gave you 10 pieces of paper and you put them on the balance to get their mass, that number would be bigger. So mass is one that the number value for it goes up as the size of the sample does. Volume is the same as that, right? If I ask you to measure the volume of a cup of water, you would get one number. If I asked you to measure the volume of an ocean of water, you would get a much, much larger number. Energy does the same thing, right? Energy depends on the amount. If I burn a match or I burn a log, the log's going to emit much more energy. It's going to get much hotter because it is going to release a larger amount of energy. All right, so in general, the larger the sample, the larger the number. And then I give you a for instance here with a glass of water. 1 glass of water weighs 100 grams. 2 glasses of water is going to weigh double that, 200 grams, because there was twice as much. Believe it or not, there are properties that the numeric values don't change even if there's more of it. These are called intensive properties. So even though the sample gets larger, like you see here, the numeric value for what you're measuring stays the same. Right? For instance, the temperature that water freezes at. Whether I have a glass of water or 2 glasses of water, when they start freezing, if I shove a thermometer in it, both thermometers will record 0 degrees Celsius. Melting is another one of these. All right. Boiling, right? If I had a pot of water boiling, or I just had a little bit of water boiling, when I put a thermometer in each of them, it's going to say 100 degrees Celsius, because it doesn't matter how big the sample is. Conductivity is a good one, right? If water conducts electricity, whether I have 1 glass of it or a swimming pool full of it, when I pump electricity into it, it will pass through it from one side to the other. These are known as intensive properties. Color is another great one, right? If you're looking at my eyes, you'll see that they're hazel, right? Whether I gain 30 pounds and I'm a lot bigger than I was before, my eyes are still hazel, right? Because it's one of those properties that doesn't change when the sample gets larger. All right, so those are your 2 styles of properties, extensive and intensive. And then your physical changes are things that alter what you look like predominantly. And your chemical changes alter who you are. Right, so when we undergo a chemical change, we give that a name. It's called a reaction. All right, and we can write equations for it that represent that chemical change. So this is equation 101 slide. All right, a chemical reaction is when one substance gets converted into something different. Like I said, you can represent it with an equation. It's a shorthand version that tells you what substances are involved and what new substances you're going to get. Right? They have sides to them, the left side and the right side of a reaction, and I've color-coded them on this slide. So my red over here are known as the reactants. They're the substances that are about to get changed, and I'm never going to be able to get them back. All right, they're known as reactants. They're about to undergo the change. Notice they're always on the left side of the arrow. Your products are the names of the things you're about to create. All right, so once we create them, they come into existence. They show up over here on the right side of an equation, right, in the green. Right? And an equation tells me a lot of different things about them. For instance, it tells me what the formula of sodium sulfate is, Na2SO4. It tells me what it looks like. That little L there means it's a liquid. Right? It tells me the CaNO3, calcium nitrate, right, is going to react with it. These two things in the real world are going to run into each other at the molecular level. They're going to collide. Right? This guy's going to look like a solid. What happens, and you'll learn this later in the year, is that basically these substances both break apart and then they rearrange themselves. So look here, the calcium that used to be with this guy now ends up with the SO4. So the Ca recombines with the SO4 and the Na ends up with the NO3. So they trade places. It's known as a replacement reaction. All right, so our reactants in this would be the NaSO4 and the CaNO3, and our products would be the NaNO3 and the CaSO4. This equation represents a chemical change, a chemical reaction. Right? And anytime a chemical reaction occurs, we can write one of these equations. All right, so that's all well and good, but how do I know this is happening? Like in the real world, I can't see all the way down to these molecules colliding. Right? There has to be something at the level that we can visualize that lets us see the sign of a reaction. And there are usually 5 different signs of a chemical reaction that we'll list. Right? I'll go through them one by one. Right? First one is evolution of heat or consumption of heat. I touch it, it gets hotter, it gets colder. They have names for them, and there's a slide coming that will tell you that. Second one, evolution of light. All right, so I put two things together, and light gets created where it didn't used to be. Third one, production of a gas or a change in odor. Right? If I make a gas, I generally will see bubbles, especially if it's contained in a liquid, and I will tend to smell that gas being created because it has different characteristics than where it came from. Like fourth one is formation of a precipitate. All right, formation of a precipitate, and that's a fancy word, so I tell you what it means. It's when I take two liquids together, and then when I pour them together, all of a sudden I see a solid form that wasn't there before. And then last but not least, a color change most often will indicate a chemical reaction, but not always, right? There are very limited, like food dyes, that'll change the color of a substance, but it doesn't indicate a chemical reaction. I just made a mixture. So some of the more fun ones, all right, are this formation of a precipitate and evolution of light. All right, so I do demos in class for all these, but for you guys at home, I found videos of me doing these or of somebody doing these that I want to take you to. All right, so I'm going to stop presenting that way because the video sound doesn't work when we do that. And I'm going to share a tab with you guys. All right, and this first one here, all right, is going to be the evolution of light. I'm going to show you what that could look like. And it's called chemical luminescence. Right, so they release light, but a lot of times heat doesn't come with it. So they'll call it cool light at times. Right, and here's some reactions that happens. All right, so I do this one in class. Right, it's showing you how they make that solution. And then it's saying we're going to add some hydrogen peroxide. And we turn the lights out. And when they mix, all of a sudden you start getting this blue luminescence of light showing up where it wasn't before. And then it eventually goes away. And when it goes away, you know it's not reacting anymore. So did a bunch. Glow sticks work the same way. Glow-in-the-dark nail polish, right, can work the same way. It's creating just a small scale, right, reaction when they see UV light. So it has to see ultraviolet light. Glow sticks, know that you have to snap them, and that's going to let those two chemicals interact. When they do, they release light. And there's a bunch of chemicals, some last longer than others. That's why you'll see a bunch of different examples. All right, so that would be a great example of what we call evolution of light or luminescence. All right, the other one I want to show you guys is this formation of a precipitate. All right, and if we're going to do that, I am going to share a different tab with you. All right, this is the one I did in class. All right, and what you're looking at here is two substances. All right, one of them is potassium nitrate. Right, the other is it's potassium iodide, and the other one is lead 2 nitrate. Okay, that was bad technique on his part. He doesn't have those labeled.
What I have here is two Erlenmeyer flasks. One has lead nitrate solids in the bottom, and one has potassium iodide solid, or salt on the bottom. I'm going to make a solution, an aqueous solution with these. So I'm going to make aqueous lead nitrate here.
Aqueous just means he's dissolving it in water.
Mixing. You can see that it makes a solution. And it does dissolve. It is definitely aqueous.
And then he did the same thing with the other one.
Now, interesting enough, lead nitrate is made of a nitrate ion. Nitrate ion is NO3 - 1. And anything combined with a nitrate ion is soluble because the nitrate ion, NO3, is 4 atoms stretched, and you have a negative
And that gets into stuff that we don't need to worry about for Gen Chem.
Let's do that.
All right, but here we're going to mix these
Here we
together.
go. Very brilliant reaction. You see that pretty, very pretty yellow precipitates.
And the precipitate is a solid.
Yellow lead paints have been known to be yellow, and also a problem. So there you go. There's a precipitate, and it's a precipitate because I know that I cannot see through the solution anymore.
And that's how he knows they're solid.
Settled for a while. We'll get something like this. This is a reaction I did about an hour or so ago, and you can see here that the clear solution is the potassium nitrate ions, or potassium and nitrate ions, and the solids are at the bottom.
He's trying to show you that you have actually a clear liquid there, and it's a yellow solid. It was a yellow precipitate. Okay. All right, so that's what's going on with what you guys were seeing in the slide here about indicators or signs of a chemical reaction. All right, so we had our evolution of heat, evolution of light, production of a gas, formation of a precipitate, and then most of the time a color change. All right, so with this idea of heat, I wanted you to know the terminology that goes behind heat, right? Again, thermic, right? Thermometer means heat, right? And then we have endo and exothermic, right? So exits, exiles, exoduses all mean coming out, leaving, forced out. So exothermic reactions are giving off heat. Right? What happens if it's exothermic? It's giving off that heat to the surroundings, so the surrounding areas will get warmer. Endothermic, endo means within. Endothermic is a physical or chemical change where we need heat for it to happen, right? Most often to break bonds, right? And if you look at this one here on the right, what's happening is we're taking two substances, mixing them together, and they need heat to react. So they take that heat from the surrounding outside them. So the heat leaves this area out here and goes into where the reaction's happening. In general, endothermic things will feel cold to the touch, because if my phone was undergoing an endothermic reaction, when I pick it up, it's going to take the heat from my hand. So my hand feels heat leaving, which we sense as cold. If there was an exothermic reaction happening in my phone when I touch it, it would feel hot because that heat being created is going to go into my hand. Right now, there's some examples that make sense, and then there's some that seem a little different. All right, so let's start with the exothermic one. Exothermic, the one that makes sense is a match burning. Right? Hey, yeah, that's giving off heat. If I touch it, it's hot. But the process of freezing, you guys associate with being cold. Right? In reality, freezing is endothermic. Heat must be given off because if you think about your phases, here's my liquid. The particles are separated and they're moving around. If I want a substance, a liquid, to become a solid, that liquid needs to lose heat so it can solidify, and it ends up forming connections between these to become the solid. So it has to lose heat to do that, which makes it exothermic because it's losing that heat. So if you have to put something in the fridge to make it happen, the fridge is simply taking the heat away from it. You can't give something cold. It's either heat leaving or heat entering. Endothermic. Generally, if things are endothermic, they would feel cold to the touch. Right? So if I melt ice, right, you would think, yeah, that makes sense. The ice is cold. It's taking heat from my hand to melt, so it goes. But cooking food is endothermic. You're going to say, wait, cooked food is hot, but realize we have to give it the heat to cook it. So that food takes in heat to cook. So that makes it endothermic. So you really just got to think of the direction that the heat goes. And all reactions, every single reaction is one of these two. It's either endothermic or exothermic. All right. All right. Last thing we wanted to talk about were elements. All right. And you guys did a worksheet where you learned names of elements, and we'll spend a little while here learning about different types of elements. But generically, certain elements have characteristics. All right. Elements can either be metals, non-metals, or metalloids. Those three categories. Right? Metals do all the things that you're used to thinking about metals. They conduct heat and electricity well. Right? Some ones you may have never heard. Malleable means I can hit it with a hammer and shape it, which we can do with metals. Right? That's how we make statues. All right, that are made of metal. That's how we can create sheet metal and things like that. Metals are shiny. That's called having luster. And then the other two have to do with wire. We know copper wire is really popular. That's what almost all wire is made of. But they have names for it. If I can pull on the metal and it becomes wire, that's known as being ductile. And if it's strong that way, they say it has good tensile strength. All metals have these characteristics. Non-metals basically are the opposite, right? What's the opposite of being a good conductor? It's being a bad conductor of heat and electricity. What's the opposite of being able to be hammered and shaped? I hit it with a hammer and it shatters. That's known as being brittle, right? What's the opposite of ductile and good tensile strength? It's non-ductile and bad tensile strength. Right? What's the opposite of shiny, luster? It's non-metals or dull. And then last but not least, there's a category that have characteristics of both. Listen, not at the same time. I can't be a good conductor of heat and a bad conductor of heat. That doesn't make sense. But what you do is you kind of pick one from each category. It's a good conductor of heat, but it's a bad conductor of electricity. It's shiny, metal property, but it's brittle. It's a non-metal property. So you mix and match. You're going to say, oh, well, like, is that good or bad? Well, it can be good, right? For instance, if you look at a computer chip, we want a computer chip to conduct electricity, to run my laptop, to run your phone, right? All of that. But we don't want it to overheat. So we don't want it to be a good conductor of heat. Right? So there is a particular element that does this very well. It conducts electricity well, but doesn't conduct heat. It's called silicon. Silicon is a metalloid, right? And we use it in a ton of design of electronics for that exact reason. All right, so the $1 million question is, well, how do I know if I'm not familiar with the element? All right, and it's controlled by the periodic table. All right, so you guys all have a copy of a periodic table. All right, but I'm going to show you on this guy here, just with coloring some things in. All right, so if I show you guys, and let me get in a view that I know what you're seeing. Don't need to share my screen anymore. And I'm going to tip it down so you look at the periodic table. All right, if you guys are looking at the periodic table, every periodic table has a line that goes around here. All right, it's known as the staircase because it looks like a flight of stairs that you could walk down. The staircase tells you where everything lives. If I live to the left of the staircase, switch to green. If I live to the left of the staircase, over here, to the left of it, I am a metal. All right, so on the bottom of this slide in class, I always tell people, like, write metals to the left of the staircase. On the right side, which I'll show you in black, these guys all right, these guys, these are our non-metals. Okay, so those are our non-metals. Okay, so you've got your metals to the left of the staircase, your non-metals to the right, and then the ones that touch the staircase, they sit above it or below it. All right, these guys here that I colored in red, these are your metalloids, right? Those are the ones that will have characteristics of each. So the questions are pretty straightforward. I could say, oh, hey, here is rhenium. And you're going to be like, I have no idea what rhenium is. Doesn't matter. Because it lives to the left of the staircase, you know it's a metal. It will have all the properties of metal. It'll conduct heat. It'll conduct electricity. It should be malleable. Right? If I picked something over here, you're like, Mr. V, I don't know anything about krypton, other than that's where Superman came from. All right. Krypton is a non-metal. You know it'll be brittle. You know it won't conduct heat and electricity. You know it's not malleable. Now, if it's a metalloid, if I pick one of these guys here in red, you wouldn't be able to predict what it is. Experience would tell us what those are. All right, so those are our three categories. You've got your metals, you've got your non-metals, and you've got your metalloids. All right, so that finishes up the PowerPoint. All right, so you guys should be good on that front. Depending on what period I have you, next up, you guys will be going into the lab, one of you, and you'll be working on a thing I posted in Google Classroom called Fundamentals of Design POGIL. So you are done with notes, and then don't forget you guys are all gearing up for a test next Tuesday or next Wednesday, depending on what period you're in. If you're in period 1, the test is next Tuesday during your double period. If you're in period 3 or 4, your test is next Wednesday in the first half of your double period. All right, so I hope this helps. Obviously, I'm looking forward to seeing you guys back at school. I hope everybody is still feeling healthy. I'm sure you're a bit stir crazy. And please don't hesitate to shoot me a message, an email, Parent Square, if you have any questions on anything.